All right, let's get started on section 1.2. We're talking about limits involving infinity. So in this section, we will see finite limits as x approaches positive or negative infinity. We're going to see the squeeze theorem again as it applies to infinite limits. We're going to see infinite limits as x approaches a, some constant value. And we're going to see some in-behavior models and also quote-unquote seeing limits as x approaches positive or negative infinity. So this video is going to be all about finite limits as x approaches positive or negative infinity. No theorems in this section, but we are going to see a definition of horizontal asymptote. So let's begin. Finite limits. The symbol for infinity, which looks kind of like this, does not represent a real number. I cannot stress that any more than right there. It doesn't express a real number. We use it more to describe the behavior. It's a descriptive word. It's like an adjective almost. When the values in the function's domain or range outgrow all finite bounds. For example, when we say the limit of f of x as x approaches infinity is some number L, what we mean is that we can force the value of the function to be as close as we wish to L by taking values of x that are sufficiently far to the right on the number line. All right. And when we say the limit of f of x approaches negative infinity as L, what we mean is we can force the value of the function to be as close as we wish to L by taking values of x that are sufficiently far to the left on the number line. So this really is talking about what's going on to the far right of a function as your x values go toward infinity, or what's going on to the far left of a function as x approaches infinity. So let's take a look at the graph of f of x equals 1 over x. And what happens as x grows large? What happens as x grows very large but negative? So over to Desmos. I have up the graph of 1 over x. As x gets very large, what do we see happening to the value of the function? So we can even zoom out quite a bit and go over, and this function is leveling out, flattening down, and let's come back over here right at 0, right? So then as x goes very large, f of x tends towards 0. As x goes toward negative infinity, I think we see kind of the same story. Yeah, that flattens out, doesn't it? So this goes towards 0 as well. And what we say here then is the limit as x goes toward infinity of this function f of x is 0. And likewise, the limit as x approaches negative infinity of this function is also 0. So when a function flattens out like this, we actually are finding something new about the function. And the new thing we're finding about it, a characteristic called a horizontal asymptote. So the line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity of that function is some number b, or the limit as x approaches negative infinity of that function is some number b. So in the previous example, since the limit as x approaches infinity of 1 over x is 0, then y equals 0 is a horizontal asymptote. And back to the question on the definition page, does the graph of f of x equals 2 plus 1 over x have a horizontal asymptote? If so, where and why? So let's go back over to Desmos and let's hide this graph. Let's go to this graph. Let's hit home. And let's see. So this is 2 plus 1 over x. As x grows very large, we see our function flattening out and leveling off. And where does it level off? It looks to me like it's leveling off at the y value of 2. What about to the left? Same story. It's leveling off at 2. This is a horizontal asymptote, and we could even type that in, y equals 2, and we can see there the green line. Yeah, absolutely. That is an asymptote of this function. So, does it have a horizontal asymptote? Our answer there is yes. Where? It's at y equals 2. Why? Because the limit as x approaches infinity of 2 plus 1 over x is 2, and the limit as x approaches negative infinity of 2 plus 1 over x is also 2. So here's an example. Use graphs and tables to find the limit as x approaches infinity of f of x, to find the limit as x approaches negative infinity of f of x, and to identify all horizontal asymptotes of f of x equals x over the square root of x squared plus 1. So we're going to use a graph and we're going to use a table to find this and to find that. So back over to Desmos. Let's hide this graph. Let's delete that one and take a look at x over x squared, x over the square root of x squared plus 1. So here it is, okay? Slightly different looking graph than the previous two examples because it seems to me that to the far right, this graph is leveling off at one value, and then to the far left, this graph is leveling off at a completely different value. What is that value? Because we were asked here for the horizontal asymptote. So I'm going to see, what does it kind of look like? It appears as though we are leveling out toward 1 as x grows large. It appears as though we're leveling out toward negative 1 as x grows small. And let's see. So if I put in a very large number, I got a table going here in Desmos, a large number like say 10. Yeah, okay, 0.99. What about 100? 0.9999. What about 1,000? Yeah, so in table, I am reaffirming my idea that y equals 1 was going to be our horizontal asymptote to the right. Well, what about a very small number? What about negative 10? Okay, negative 0.99. Negative 100? Negative 0.99995, and negative 1,000. Again, same story. So it looks like by table, we are confirming what we saw by graph. And so that means we need to give some answers. The limit as x goes to infinity of this function was 1. And the limit as x goes toward negative infinity of this function was negative 1. And we have horizontal asymptotes at y equals 1 and y equals negative 1. Important things to note here before we end this video. Asymptotes are lines. So we need to write them as such. If you just say a number, there's an asymptote at 1, there's an asymptote at negative 1, you're not telling a whole story. So we need to tell the whole entire equation of a line. Y equals some number, okay? Second of all, while many functions do have the same horizontal asymptote toward infinity as they do toward negative infinity, it is not necessarily true that they always do. For instance, this function here, we had different horizontal asymptotes to the left and to the right. I'll see you for video 2.